And finally, I'm able to talk about the famous simultaneous diophantine approximation theorem due to Dirichlet. In 1842, the theorem says, let A be an M by N matrix with real values and let Q be a real number greater than 1. Then there exists an integer vector P in Zm and an integer vector Q in Zn with the maximum norm or the infinity norm, namely the biggest absolute value of its components, with this norm strictly bigger than 0 and less than Q, such that still the infinite norm of this vector AQ minus P is bounded by 1 over Q raised to the power N divided by M. This tells you can put a uniform bound for this diophantine approximation. So how is this theorem related to the Minkowski's linear form theorem? Actually, I should point out that Dirichlet stated and proved the theorem before Minkowski. So in the original form of Dirichlet's simultaneous diophantine approximation theorem, this Q was an integer, and he used a different method. And Minkowski was able to prove it for any real number greater than 1, not just an integer, by using his linear form theorem, which is a corollary of convex body theorem. So how would you translate this into the language of the linear form theorem? The translation goes like follows. So if you look at this condition, if you look at it component-wise, it says the absolute value of this is less than or equal to 1 over Q raised to the power N divided by N for any I from 1 to M. And this condition says each component Q sub k is less than Q for any k greater or equal to 1 less than or equal to n. Does this remind you of the Minkowski linear form theorem? Yes. Specifically, we are talking about this corollary of linear form theorem. Here, this guy plays a role of R sub I, and this guy plays a role of R sub k in the linear form theorem. And you observe that in this situation, those alpha sub i's and those alpha sub k's will have the product equal to 1. Because if you raise this guy to the power n and raise this q to the power n, you get precisely 1. This allows you to use that corollary of linear form theorem. Now the key question will be, what is A as in the Minkowski's linear form theorem, or rather its corollary? What do you think the m plus n by m plus n matrix A will be? As in the corollary of linear form theorem. This is the most interesting part of this proof. I'll let you think about it on your own for a while, and I will tell the answer anyway, later. So this is how you're going to choose A. Choose A, quoted A, not the A in the Dirichlet's theorem. Choose this quoted A in the Minkowski linear form theorem as this matrix consisting of 4 blocks with this A, which is a m by n matrix, exactly the same as this A. And now, by the corollary above of Minkowski's linear form theorem, there exists an integer vector p in Zm and q in Zn. Maybe I should put negative sign here, such that this matrix applied to this vector has components satisfying those inequalities. Because if you do the block computation, this precisely gives you negative p plus a applied to q, and the second guy will be just q, which component-wise will be precisely those guys. And as a result, if you translate back, you get first the maximum norm of q is less than q, capital Q, and second, this norm still maximum norm is less than or equal to 1 over q raised to the power n over m. This is almost what we want at the beginning, except that we also require this q to be non-zero. So the question is, why is Q non-zero. Q is non-zero because if Q is indeed zero, then what will happen? If Q is indeed zero, then this part will be zero. And as a result, each component of P sub I, will be less than or equal to 1 over this guy. But however, this Q is greater than 1. Because Q is greater than 1, this is strictly less than 1 for each I. So this forces P sub I to be equal to 0 for any I, because P sub I is an integer. So this is a contradiction to this corollary of Minkowski's linear form theorem. Because don't forget that the Minkowski linear form theorem has a conclusion that actually this vector is non-zero. This vector in z raised to power n plus n is a non-zero vector. I should have said it earlier. So anyway, this is a contradiction to the corollary. And this completes the proof of Dirichlet's simultaneous diophantine approximation. Because now we can conclude that this Q is also non-zero. This is exactly what is stated in the Dirichlet theorem. The hypothesis that Q is greater than 1 is used here.